Awesome. Thank you so much for having me. Thank you guys for being here in the afternoon of Friday. Since I know I am between you and your weekend, I'm going to try and keep this engaging. Also, because we have a rather intimate audience here, I really encourage you to ask me any and all questions. Today, I'm going to be talking about topics related to Euclidean neural networks. These are neural networks that understand the symmetries of 3D space, so 3D translation, 3D rotation, as well as mirrors. So a bit of a roadmap. So I have my slides here in case that is of interest to you. So just tinyurl.com/test-harvard-bigdata-2025. That can be useful in case there's like a particular reference on a particular slide that you may want to have for later. And you can see that I'm a bit of a clutter bug in terms of backup slides. So for the 50 or something slides that you'll see today, there's like 100 in backup. So in case you, I don't know, ever want something to look at. Okay, so let's get to what I'm actually going to be talking about today. So first, I'll give a brief motivation for generally what we're hoping for that AI will help us out in the atomistic sciences. This is going to echo a lot of what Trevor already laid out beautifully in his talk. Then I'm going to talk about generally how do we build symmetries and what symmetries are into neural networks and kind of motivate that this is standard practice when it comes to building neural networks. We control the interactions between our data, and by doing so, we actually often give rise to various symmetries. I'll talk some properties of Euclidean neural networks, and then I'm going to focus mostly on two different applications. We'll talk about interatomic potentials, again, what Trevor was talking about a bit earlier, essentially like given an arrangement of atoms, what is the energy of that configuration, and do the atoms experience any forces due to interacting with one another? And then generative models. So this would be generating atomistic structures. So I'll specifically talk about some molecules and some proteins. If we have time, which we may or may not, I can go a little bit of a deep dive between some of the nitty-gritty details that determine a lot of the computational efficiency versus expressivity of these types of models, which would be encoded in their tensor products. So with that wide smattering of topics, let's go forth. Takeaway, yeah, I always like to give you the takeaway from the start, is building the context of your data, in this case for atomistic sciences, but equally valid in whatever domain is interesting to you. By building the context of your data into your learned model, there are caveats for often you have to work a little bit harder to get those models to work, as far as like learning how to optimize them properly. There might be some computational overhead, but generally you're going to see that this improves the generalization of your models, the data efficiency, and you can get rigorous guarantees. So, okay, that was a lot of words. Let's go forth. So first, I want to define what an atomistic system is in the context of this talk. I just mean anything made of atoms, which generally is everything, but we tend to break them down into various classes, some of which are like crystals. So these are periodic arrangements of atoms described by a box filled with stuff, and then we tile the box in space. These are two of my favorite crystals from my PhD thesis. This is a very humble silicon crystal. We have molecules, so we can either have sort of the graph representation of the molecule, which is very popular, or kind of a 3D representation in which the molecule is actually jittering around at temperature. So molecules are kind of more bendy, so that's why we tend to think of them more as graphs. Crystals are also vibrating, but they tend to stay more in the same place, which is why we tend to like this representation for crystals. And then you have things from structural biology. You have proteins. Maybe you care about how molecules are interacting with proteins. Maybe you care about RNA. Crystals, as Trevor was talking about, can have very interesting magnetic texture to them. And then you can have kind of like hybrid systems of like, how does this slab of a crystal interact with this molecule? Or you can have things that are like kind of periodic, but are truncated like nanocrystals. So it's really a zoo out there, but in the end, it's all atoms. So I'm going to say a broad statement that has a lot of caveats, but for the purpose of this talk, this is mostly correct. We have traditional techniques that we can take where the atoms are at, and using these traditional techniques and a lot of compute, so quantum theory and supercomputers, we can get the properties of a given arrangement of atoms. There's caveats to that. Certain properties we're good at, certain properties not so good at. So don't ask me about excited state calculations. But if you want a general thing of like, where are the electrons at and what are they doing, we are generally pretty good at that. Other caveats being, as long as you're not asking about too many atoms, and as long as you're not asking me about properties that require very long timescales. As I said, though, these calculations, whether they're first principles or whether you are doing things with molecular dynamics, they take a long time. And that's a bottleneck to us making progress, exploring material structures, and so forth. Again, things that Trevor touched upon already. So what do we want from machine learning or AI or deep learning, whichever flavor that you'd like to do? We would like to speed up these time-consuming calculations. We would actually also like to do inverse design of given properties that I want. What are materials that we can potentially make that have those properties? There's also a general need for hypothesizing new structures. Maybe we're open to properties that we're not even aware of, but we just would like some more ideas on what might be possibly stable in the realm of atomistic systems. And then I think something that really is at the crux of all this is that we'd really like a map to see where we've been, where we're going, and what properties we may find.
I have a naive question.
Yes, please, please.
You do a computation and
Yes.
you come up with a new structure.
Yes,
You computationally says it has interesting properties.
yes.
Now, how do you know how to fabricate it? How do you make it?
Super great question. Okay, so this is a question of synthesizability, and it is one of the caveats I am currently sweeping under the rug. Synthesizability is a word that people say, but it means something different to every single type of scientist. If I'm a semiconductor physicist, if it's synthesizable, I am leveraging the trillions and trillions of dollars that have gone into the semiconductor industry, and I'm saying, oh yeah, that's synthesizable. And I'm like, that's synthesizable conditioned on having access to all of this amazing infrastructure. If I'm an organic chemist, it's like, okay, I know how to take this molecule, kind of break it into different steps and make it from these precursors. So the answer to your question is, we don't know. Or it depends who you ask and what it is. Okay, great question. Any other questions while I'm here? Keep them coming. I love them. I don't need to get through my slides. I already know what they're going to say. So, all right, key challenges. If we would like to do this, how do we go about representing atomic structures to machine learning methods? And how does the way we want to represent the physical world inform how we build our methods kind of from the ground up? And then what application does that enable? And I won't talk about this too much. I'll kind of sprinkle it throughout the talk. What are some maybe unexpected consequences of building in the assumptions that we have into these methods? So those are just some things we'll talk about. Okay, so first I want to talk about neural networks. Neural networks are often stated as universal function approximators. We're going to just call them function approximators, but there's a lot of devil in the details here, because when we're really making a neural network, we're architecting what pieces of information are allowed to interact with what. So here's some examples for different types of neural networks. So what is often quoted as the vanilla neural network or the typical neural network is a dense neural network, which uses matrix multiplication. So if I have my x's are going to be in orange, and my w's, which are the weights of the model, the learned parameters, are going to be in blue. So I have my x, I have my matrix w, ka-chunk, I get some output y, and I might push that through some sort of activation function, often called a nonlinearity. Now, despite the fact people think of this as like making no assumptions, there's actually a lot of assumptions made in here. We're assuming that the features are independent, that they aren't needing to travel together in any sort of way, that they're fixed lengths, so that my input feature vector is not changing size, and that my features are ordered, because all these weights are sensitive to the position of everything in there. So that's an assumption that's sort of built in there. And I'm just going to abbreviate kind of WX, just mathematical notation. Okay, let's kind of move on to sort of another flavor of neural network that's very popular, and that of convolutional neural networks. And this is typically applied to images, which introduces the notion of geometric relationship of different numerical values, so different pixels being next to each other. In a convolutional neural network, we have a filter made of some, let's say, 3x3 pixel, if it's 2D. And that pixel, those filters are applied uniformly across the entire image, creating a new convolution map. So if I were to apply this filter onto this centering of the pixels, and I get 1 pixel out. This is encoding quite a lot of information. First of all, it's implying that the same feature, whatever feature I'm trying to identify with this filter, can be found anywhere in the image. There's also, in the machine learning context, convolutions, of course, don't have to be local in a mathematical context, but in machine learning, they're always non-zero here and 0 elsewhere. There's a strong notion of locality. So pixels that are close together are more important. There's a very strong prior that we're imposing on the model. And here I'm just notating that we have some function, this filter function W depends on the relative positions of 2 pixels and what is at a given location. Okay, transformers. This is what's behind things like ChatGPT, any other favorite transformer, vision transformers, anything. And it's the notion that we want to pay attention on the impact of every token, so every piece of our input, on every other piece of our input. And furthermore, we will often add what are called positional encodings, common positional encodings. You could say this is 0, 1, 2, 3, 4. Actually, what is most often done is that people use a Fourier basis. So heavily inspired by math. So you'll typically append some sort of evaluation of some sine functions with some periodicity, and you'll attach that to whatever data is in your whatever your data is. So if it's an encoding of a word, so you'd have the encoding of the word and you'd have like where it is in the sentence. And so this is actually very similar to the convolutional case. What's different here is that not only do I depend on like the relative positional embeddings, I also care at who is looking at whom. And so this attention function that is in transformers, it kind of plays a similar role to a filter. It depends on this who's looking at whom and not purely just based on the geometry. So there's actually a lot of structure in transformers, which I think is part of the reason why they're so successful. Last but not least, I'm going to try and convince you that Euclidean neural networks are very appropriate when dealing with 3D data. Now, what is special about 3D data is that in order to articulate where things are in 3D space, I have to first lay down a coordinate system. And we'll talk more about that later, but basically we want to make sure that if I change my coordinate system, my model is not thrown off by it. Okay. The big point here is that this is essentially encoding whether or not there are certain symmetries of your data. So for a dense neural network, we don't really have any symmetry, and in fact, we have a lot of canonical ordering. We have translation symmetry for convolutional neural networks. You actually can have permutation symmetry for transformers, depending on how you do your positional encodings. And then last but not least, we will have Euclidean symmetry for Euclidean neural networks. Okay, great. So coordinate systems are useful for describing physical systems, for where things are in 3D space. Any type of property that depends on direction. So if I'm an atom and I'm experiencing a force, this is articulated by a vector. Maybe I have this coffee cup and I probably shouldn't spin it, but if I did, the motion of that object or how easy it is to spin it would be described by a moment of inertia tensor, which is a 3x3 matrix. We can consider how a material acts to being squished and stretched in various directions, and that would be like an elasticity tensor. And then for those of you who love anti-symmetry, here is a Levi-Civita tensor, a nice 3x3x3 tensor in 3D. We additionally have tensor fields. So we can have scalar fields like energy, pressure, that can be a function of a collection of variables, vector fields, useful for describing velocity fields and fluid dynamics. And you can have matrix and tensor fields. This is particularly true for strain fields and materials. So 3D coordinate systems, if you're in 3D, very useful. However, they're fundamentally arbitrary. So if I have this assembly of atoms and I have coordinate system 1 and coordinate system 2, it's really important to note that if I were to describe where the atoms are according to this coordinate system versus this coordinate system, numerically those look completely different. And yet we're describing the same physical system. So what's going on, the idea here is that numerically these are distinct descriptions, but I can transform between them by the symmetries of 3D space. So translation, rotation, and if I went from a right-handed coordinate system to a left-handed coordinate system, I could even include inversion. But a traditional machine learning model we'll not be able to see that these are actually the same system described differently. Now, in order to use 3D coordinates, which are useful but not be biased by the coordinate system, we have to kind of build this in. So can we do this? And this is what equivariant models, so in this case, 3D Euclidean equivariant neural networks, aim to solve. So a neural network that is equivariant to this Euclidean symmetry sees 1 and 2 automatically as the same system, just described differently, even without training. So this is a property of basically this function space of neural networks. And this is the property that it encodes. There's a nice commutative diagram. So if my function f, my neural network, regardless of what weights it has, if I push this structure through the function, and let's say I'm predicting little vectors that are forces, and then I were to rotate my system, that is equivalent to me rotating my system and then pushing it through the function. And this is the definition of what is called equivariance. So it is a useful definition, but it doesn't really tell you how we do it. But this is, in fact, just the definition of the property that we seek to have in these models. Any questions here before I continue? I haven't really told you how we do it. Okay. So why is this nice? Well, I'm showing you atoms, but this is true for any 3D system. So I could be talking about a mesh of a bunny rabbit. I could be talking about fluid flows. I could be talking about the structure of galaxy formation in the universe. As long as we're not going too fast and we're not near any black holes, then 3D symmetry is equally useful here. And so it's a nice constraint to be able to build into your model. Yes?
Would it be helpful for, I don't know, galactical systems to have, I don't know, like spherical coordinates, or are they equivalent on this?
Great question. Okay, so whether or not we're using spherical coordinate versus Cartesian. Yeah, so it shouldn't really matter. I think Cartesian is nicer in this particular case because of how we do the computation, but like you certainly can express a lot of this stuff into spherical coordinates, but we tend to build the models using Cartesian systems. But it should be equivalent. There should be an equivalent formulation, but it's kind of extra nice to do it in Cartesian. Yeah.
The motivation for doing everything is you're basically studying atoms.
I guess the motivation here is that we just have things in 3D, and my personal motivation for getting into this at all was atoms, just because I was coming from materials physics personally. But this is equally relevant at other length scales as well. Certainly, we deal a lot with relative distance vectors. And so you still can have that notion of having like kind of a center to like maybe a galactic center or something. So in other use cases, when I'm collaborating with like folks in astrophysics, like sometimes we will put a point, like a special point that has like a special encoding that would indicate a galactic center, because that is a very nice relative distance vector to have available for the model. Great question. Hi.
Intuition for like when you should do this for like the crystal or maybe the bunny example.
Yeah.
For the fluid flow, I'm not so sure. What's the advantage of that?
Yeah, so I guess on one hand, so there's a notion of like global equivariance, that if I rotate the entire system, this is true. But if we go back to even like kind of the convolutional picture where we have these local filters that are looking at patterns, this is very much the case, because in this fluid flow, like as we kind of see it blooming off to the side, we have these vortices, and these vortices will reappear in different orientations and locations. And so being able to, I only need to see that pattern once, and then I can automatically identify it in other orientations, that's really helpful. And then if I see like pattern A and pattern B interact with each other, I can still say this is pattern A, pattern B, and then I can be sensitive to what's the relative orientation of these two patterns, rather than thinking that this particular configuration and this particular configuration are like completely different. So even being able to have that local equivariance, we believe it to be quite useful. It's notoriously hard to actually tease out the benefit of local, like local and global versus just global. But we suspect it's the local equivariance that's really what's helpful, especially for atomistic systems when we have like local environments. Great question. Thanks. All right, here's a first consequence of equivariance. Now, again, I'm kind of just dropping you into this. I'm not kind of formally deriving how this arises, but a consequence of being in 3D space, being data in 3D space, is that if you give me data and you tell me, Tess, this data transforms predictably if I were to rotate it, translate it, mirror it, and I'm like, super, I provably can take your data and break it up into more fundamental pieces known as irreducible representations. And we're gonna mod out translation for the moment and just talk about rotation and mirrors. Provably, I can break up your data into these data types, these irreps, that are indexed by an angular frequency, essentially how quickly does your data rotate with a rotation of the coordinate system? Does it rotate? Not at all. Angular frequency 0. Does it rotate at the same rate as a rotation of the coordinate system? At double the frequency? 3 times the frequency, and so forth. So you have like an angular frequency associated with the data. And then, and this comes from having inversion, so having the combination of rotations and inversions would be mirrors, is whether or not your data flips sign when I go from a right-handed to a left-handed coordinate system. Let's go with some concrete examples. Let's start with things that have 0 angular frequency, so they don't change under rotation, but they might change under inversion. So if I have a picture, and it's a picture of a rabbit, that is a classification label. That classification label does not change if I rotate. It does not change if I mirror the rabbit. It is still a rabbit. It might look slightly different. So this is a scalar. It is even parity. However, if I have a picture of a hand, and I'm saying this is a picture of a right hand, and then I mirror the image, well, now it's a picture of a left hand. And so it's still a hand, so it's still a scalar. It doesn't really change if I rotate, but it does change if I flip the image. Let's go to vectors. So you're familiar with vectors. We use these to describe coordinates. Then there's its even parity neighbor, which is pseudovector. And actually, you guys are all familiar with pseudovectors. It's the result of a cross product. So if I take x cross y, I get z. If I take negative x cross negative y, I still get z. So we don't usually like play around with pseudovectors directly, but they do arise from the interactions of things like vectors. Last but not least, I'll just briefly show these. You can have a notion of like something that has a twofold symmetry, like a double-headed ray. So if I care about the x direction, but I don't care about whether it's minus x or positive x. And then things like helices, you can also rotate them by 180 degrees. But again, if you mirror them, it goes from a left-handed helix to a right-handed helix. And there are generalizations of this. Imagine like 3-headed rays, and I don't know how to picture the generalization of the helix for L equals 3, but it also exists. So the reason I'm going through this is to show you that, well, these weird data types turn out to match beautifully with a bunch of ways that we represent physical systems. So we talked a little bit about vectors. Atomic orbitals, which have a component that transforms as a spherical harmonic, so very special functions to the 3D rotation group. So s orbitals, p orbitals, d orbitals, s, p, d, f. These all have a particular transformation that matches one of these irreducible representations. So in fact, by encoding 3D symmetry, we actually have naturally encoded the data types of how we describe many things of atomic systems. There's even more complex objects, such as Hamiltonians. So these are interaction coefficients between different orbitals. I'll show a subset on the next slide, so I'll just highlight this really quick. There's even different ways that molecules vibrate. So if I had a little hexagonal molecule, there are certain ways in which molecules will vibrate at a finite temperature. And you can even break apart these random vibrations into distinct vibrations that transform as these irreps. And spectroscopists use this a lot for understanding, like, what are they looking at? Because there's a lot of selection rules. Okay, I want to zoom in a little bit on one of these interactions. So suppose I have I guess one thing else I want to say. The reason I'm picturing this rotating is that it's pretty easy to see that this water molecule is rotating. But what this is the Hamiltonian matrix. This is the interaction matrix for that given orientation of the water molecule. But it's not saying anything different. The point is, this is easy to see how it's rotating. This is rotating in a very messy way. You really don't want your model to have to learn this. You'd rather it focus on quantum mechanics than have to learn this. It can, You can teach a model to do anything, but I'd rather it focus on the quantum mechanics. Okay, so let's go to like a p orbital and a p orbital interaction. So p orbitals are basically the same thing as vectors. So if I have a vector-vector interaction, all the different ways that a 3D vector and a 3D vector can interact creates a 3x3 matrix. Now, how do we map that onto these irreducible representations? Well, it actually breaks apart in the following way. So the trace of this matrix is a scalar. It is invariant under rotation. The anti-symmetric part of this matrix corresponds to what you get from the cross product. So it's actually a pseudo-vector. And then last but not least, the symmetric traceless part of this matrix, so kind of the symmetric part modulo the dot product, that is going to be an L equals 2 even parity object. So this is just an example to show that you can take a more complicated object and break it into these different pieces. So this is kind of highlighting where these components are in the matrix. And this is just showing that you have 9 degrees of freedom over here. You have 1, 3, 5, 9 degrees of freedom over here. So this is a information preserving transformation. Okay. So that's all I'm going to tell you regarding kind of some of the inner workings directly. I thought next I would talk a little bit about applications. Any questions before we go there?
I think I'm a bit.
Yeah. So how comfortable are you with like convolutional neural networks? Super, okay. So the biggest things that change, Hansaroma shock, okay, great. So essentially, if we're gonna do like a convolutional neural network, you're gonna have some input times some function. So we'll have input on like pixel I, and we're gonna have maybe the relative distance between some other pixel J. And actually, let's do this. No, we can use dummy indices. We're gonna sum over all I that's in the neighborhood of J, and this is gonna equal kind of the output on J. So I have some input, so this is just a number that is like some pixel on point I. I have the relative distance between these, and I have this function here. And then that's gonna go to the output. What's gonna change here is now all of these objects have to be promoted to these irreducible representations, and we can't just do multiplication anymore. So what we're gonna end up doing is that we're gonna have this I has now an implied L and P. I'm gonna put Pi. We're gonna do a tensor product. My filter will actually carry one of these irrep indices. And I'm gonna be a little bit fast and loose with this. So this is L of the filter dependent on Li and L out. And there's M's and things. And I'm just gonna do concrete notation. And this thing here, if you're familiar with Clebsch-Gordon coefficients, that's what's hiding in here. And so that's an example of how you would promote a standard convolutional neural network operation to kind of a equivariant version. Now that's just one of the operations. You can do this to any operation for a neural network, but this is kind of, you start having a bunch of indices that you have to account for. And fortunately we've made code to do this so you don't have to. But yeah, hopefully that helps a little bit. Yes.
So another way to deal with these symmetries. So if you want to deal with translation, you just put the mean of your position.
Either the mean of the object or you only deal with relative vectors, which is what we prefer to do. Yeah, either one's good though.
Yeah. The way to deal with rotation is to put your object in a canonical.
Yes, canonicalization.
Now that's something that happened. That was pretty machine learning.
Yeah.
We are building a search engine for 3D objects.
Yeah.
And we exactly to be able to deal with this rotation, we would use PCA on the point on the object to find a canonical position.
Yes. Okay. Beautiful question. What about canonicalization? Why don't you canonicalize? Okay. So you could, for example, look at the principal axes of a molecule and try to orient along that. This gets a little tricky with infinite stuff, but the primary reason why we don't necessarily do this, people do try this, people do this. So there are camps of people who use canonicalization. There's a student who I work with, Hannah Lawrence, and she and collaborators have a paper about how no canonicalization in the context of this sort of stuff is smooth. So there's no way you can define a canonicalization that doesn't have some discontinuity. That tends to make me uncomfortable as a physicist. I like to avoid my discontinuities as much as possible, but you can do it. However, we choose not to here and instead build in the symmetry so that we can choose any representation and it'll just be treated appropriately. But you're totally right that canonicalization is an option. It can get a little dicey because, like, let's say I have a molecule and, this might be degenerate along 3 different directions, like all these directions are equivalent. So I'll have to choose something, that's fine. But then what if I, attach something here? And then what if I attach something here? So it can get such that I start adding things and it causes this discontinuity in the canonicalization if I was using something like principal components based on where the geometry is. And that might be undesirable because it makes it harder to see when things are similar. It won't work, right? Enough care and feeding of a model and you can achieve, I think, pretty much anything. Yeah.
The other thing is that, so with your cup, so the cup you have on the table.
Yes.
This would be not very good because of.
It has a rotational symmetry. You will have degenerate eigenvalues, but you can still sample and then any of those are valid.
Yeah.
So, I mean, I think the symmetric case is actually, I'm less worried about that because then it's like, great, sample anyone, they're equally good, you're good to go.
You can still do that with object having multiple eigenvalues.
Yes,
Yeah.
exactly. Yeah. No, so I agree that I think the degeneracy is maybe not the issue. It's the issue of how, if I think that I want this molecule and this molecule with this to be similar and they suddenly have very different coordinate frames, it might make it harder. So, okay, great questions. Thank you guys. Okay. Let's talk a little bit about applications. So these types of models have been successfully used for a variety of things, whether it's predicting energies, forces, or vibrational modes, also known as phonons in the context of crystals, because we like the suffix of on for everything. We like everything to be a quasi-particle, or whether it's charge densities or Hamiltonians. Hamiltonian is that kind of matrix that I was showing you earlier. And there's also more geometric tasks like generating new geometry, whether it's maybe coarse graining, so maybe having a simpler version of a atomic system for the sake of speed, and then being able to go back to fine-grained coordinates, or generating something from scratch. So I'm going to focus on these 2 tasks of specifically predicting forces, because I think it showcases a lot of where the rubber meets the road kind of issues, and then also talk about some generative modeling stuff that I hope you will find interesting, because I think representationally it's interesting. Question? Yes. Nonlinearities also have to be dealt with specially. So one of the easiest things is you can't just apply ReLU, because if I have a vector and I apply ReLU, it depends on the orientation. So you either only apply things to the norm, or you can project things to real space, which induces it as a permutation representation, and then you can apply ReLU, because if you can apply any nonlinearity to, I mean, I'm going very fast to answer your question, but it's a great question, and there are a variety of tricks for doing this, and going to real space is one of them, and the other one is only dealing with norms in some form or another. Okay, so probably the first demonstrated use case of equivariant neural networks, because a lot of people were suspicious, will these things even train? They're so complicated, was interatomic potentials. And this is the case of, I have a arrangement of atoms, I'm gonna push them through this neural network and get an energy. I'm gonna train this model based on computationally expensive either density functional theory calculations, coupled cluster, choose your favorite method that you can get enough data for. And then to get forces, one thing we really like is we like our forces to be conservative, and the easiest way to do that is to just use auto differentiation built into neural networks to get the forces as a derivative of energy with respect to the positions. I am missing a minus sign. The minus sign will come back soon. So this is one way to do it. There's an active debate in the community as to whether you need to do this, because this is expensive. Because you do this, you get the forces, and then you have to backprop through all of this. So you're doing like a triple backprop. And if you need to do vibrational frequencies, which is another derivative, then you're doing 4. So this can get a bit obnoxious, but this is still sort of best practice for ensuring that you're getting forces that will play nicely as you do longer molecular dynamic simulations. But some people also just directly predict forces. Yes?
Yeah, I'm completely naive, but would it be possible to do numerical differentiation? Even though the back propagation will be analytic.
Yes.
The numerical stuff might be very fast.
Yeah, so I guess this is with respect to updating the model. Can you do numeric? I think, would that be faster? This is a question that I would hope that I would have the answer to, and I'm blanking. Is just running it forward to get the gradient faster? That's a good question. I'm not sure. It's not what we, it might not be. That might not be accurate. Well, if you make it small enough, I don't know. It probably also depends what floating accuracy we're going at, but that's a great question. I will endeavor to have a better answer for you, but yeah, I suspect the answer from the kind folk behind you is probably spot on. Yeah, so we tend to use it with autograd. It is possible maybe we could do numerical. So kind of an example of some of the zoo of models that use equivariance would be Nequip and Allegro, which are born from the Mirror group here at Harvard, Boris Kaczynski's group. They are experts in this stuff. Then there's also Mace from Gawarchani and friends over at Cambridge and other folks. And there's also TorchMDNet. So there's a whole zoo of people who have made these models work on diverse systems. In my own group, and with our wonderful collaborators at Meta, we've built a model called Equiformer, throwing our hat into the ring. We're on version 2, soon to be version 3, because there's always improvements that you can make. And the idea with this model is that we wanted to make an equivariant transformer that worked well for force prediction. So we're kind of combining this expressive attention aspect of transformers with what you need to preserve 3D equivariance. And I'm not going to go through too much of the details, but kind of as we discussed here with how do you promote a regular old convolution to an equivariant one, you could imagine going through kind of a similar process with an attention mechanism that you need to basically say, I'm going to replace all the multiplication operations with these tensor products and Clebsch-Gordon contractions. And that pretty much gets you most of the way there. Plus, turns out normalization becomes extremely important, especially as you build bigger models. The point here is that this was the first equivariant transformer that became a top performer across multiple different data sets. So there were the Open Catalysis 2020 data set. So these are catalytic. So this is solid state slabs with molecules on top. The purpose here is to try and aid heterogeneous catalysis, which is responsible for like 80 to 90% by volume of all chemical products in the world involve some form of heterogeneous catalysis to produce. So that's why people care about it. So it was doing well on like this data set, a later data set that's similar, and then ODAC is actually a data set that has these very porous metal organic frameworks, but doing a similar catalysis task. Yes?
That I want to mention this token phase to this one in one frame of reference, and basically when you do data, the same attention, you're going to get the same attention rate. That's
right, yeah. So if I have my system, how much I'm attending, because like attention kind of is a scalar quantity, how much I'm paying attention to something, although you can have like vectors coming out, but yeah, it shouldn't change, but it might be a very nonlinear kind of function going on to how you evaluate attention. So maybe what you're using to evaluate how much you attend to something could be quite complicated and vectorial or tensorial, but it will boil down to a scalar quantity. Yes, yeah. And we might formulate it slightly different, but so instead of like a dot product, we might do tensor products and other things, and yeah, but that's kind of the gist of it. Okay, so this was Equiformer and it was doing really well. Another thing that I think is super interesting is that there's all these sort of self-supervised tasks. Trevor was talking about how important self-supervision can be and how it can really give you more bang for your buck. You don't even need more data. You just use what you have lying around and just use it more effectively. And this is an example for denoising. So first I owe you an explanation for denoising, and I'm watching the time. Okay. So for denoising, the idea is that you're still training a model that's going to predict forces, but maybe what you do is, let's take our, please don't call the chemistry police on me. We take our molecule, and not only is my model going to predict forces, but I'm actually going to move these atoms and let's say this molecule is stable, I'm going to move these atoms, I'm going to feed it to the model, and the model is supposed to move them back into a happy equilibrium configuration. So I noise the molecule, I feed it through the network, and it puts the atoms back where it's supposed to be. So this is called denoising, and it was used, it's been used before, and it improves models. But the thing is, when we're doing molecular dynamics tasks, we mostly have structures that are already unhappy. So they already have little force vectors on them. So how do you noise it? So if I move the atoms, well, we want to return to a structure that has forces on it. But the thing is, we need to give it a little bit more information. And so we figured out a procedure to denoise non-equilibrium structures, and it turns out that is actually quite helpful for training. So what essentially happens here is that we will noise the non-equilibrium structure, and then when we feed it to the model, we not only give it the noised structure, we give it force labels. So saying like, you know, I want F equals blah, blah, blah. So it's like this atom should have a force of this. This atom should have a force of this. And this is data you already have from your training data. And that way, we're not only saying denoise it, we're saying denoise to a structure that has these forces. So if this was the equilibrium version saying I denoise, or I noise the structure and then I denoise, this is saying I noise, I give you some force labels, and then I denoise. So we give the force encoding, and then we're able to go back. Okay, the point here is that with denoising, you can reach a comparable accuracy to using twice as much train time. So if I have 30 epochs here, so I ran the model through 30 epochs, I'm able to use 12 epochs to achieve better forces for not very much cost, additional cost and training, versus this is, you know, more than double. And so this is a practical thing that people can do to get more out of their data. Okay. Now, another question we have, oh no, Teddy's face is blocked. Can I move? Okay, there's Teddy. Here's Teddy. Teddy had a question. He's like, well, this is really frustrating. We have like, I mean, it's great that we have these universal models that can do these interatomic potentials, but they're getting so big that if a grad student just wants to train something from scratch on a custom data set or just wants to play around, there's not really a good option. Like, we don't all have the compute resources of Meta. Is there some way that we can do some training tweaks, some good, you know, care and attention to our models in order to get a smaller model that is close to being as effective, maybe not the top performer, but up there? And so the short answer is we can. And this is just some text, but I'll kind of go through the most of it. So NeQuip was the hippo one that's over here, that's made by Boris Kaczynski's group. So NeQuip is a great model. It's been really hard to beat. And so what we did is we said, let's start with NeQuip and do some sort of modification, some kind of different ways in which we normalize, but it's still structurally pretty much the same model. And what we're going to do is we're going to not use very many parameters. So the equiformer model I was just talking to you about, it has about 100 million parameters. This one has less than 1 million. And it only takes far less than a quarter. So equiformer took a lot of hours of training, but even some of the other top performers were already at less than a quarter of the time, something that'll take a couple days on about 8 GPUs, which, you know, it's still a lot of compute, but it's not unreasonable. And currently its ranking is number 4 as of today. You always have to check these things. It was 3 on Monday, but it's 4 today on a particular discovery data set, which I'll show next. The inference is about 10 times faster, so it's faster to run, and we have open source weights and reproducible JAX code, and soon coming to PyTorch. So really the goal of this was like just to see, can we make a model that's nice and compact and practical? So some things for train time. So here are some other kind of models that it's kind of, that'll be on the next slide, but just to kind of show we're at 500, and here's some training times for other ones. So, you know, it's not many, many orders of magnitude less, but it's to the point where you can make some more progress. Okay, here's MapBench Discovery. This is going to be from the Materials Project Trajectory data set. And just to give you a sense of kind of like the zoo of things going on, so this is one of the models we were comparing against. Here's MACE, here's Equiformer V2 with a particular training. ESEN was recently released from Meta. So this is their 30 million parameter model. So again, a lot of these are going to be ranging more in the 10 million and higher. And yeah, they have kind of there's many different ways to weigh these models. I'm not going to go into all those details, but all of these different metrics do matter, and it's great that we have all these different metrics, but we try to have some sort of combined score here. So just to show that it's basically competing up in the top 5, and it has substantially less parameters, and it's reasonable for a single grad student to train. This is just some fun results. So actually, there was this really nice paper from O'Neill et al. Showing that even if you train just on materials relaxations and you've never really seen many water, like not that much molecular dynamics of water, you can actually still model the dissolution of salt in water. So that's kind of nice. So Teddy tried that with Niquix. And then this is also showing just a structural relaxation with for a metal organic framework. So just showing that it can actually do stable things and not explode. Quick training tips. I'm just going to highlight these just in case this is relevant for you. There's a lot of devil in the detail sort of stuff. One of them that was actually kind of interesting and surprising, which has gotten a lot of attention in the large language model community, is this new optimizer called Muon, which basically tries to do a better job of approximating gradients pertaining to the performance of a function and not just like this gradient with respect to the parameters. I will not give much more details than that because that's kind of the level of my understanding. But it's just really interesting to see there's still a lot that we can benefit from better optimizers in the ML space. But there's also a lot of kind of practical things like when you do your batches, making sure it's balanced so that you have roughly the same number of atoms when you're batching, or you want to make sure that you're not able to overfit to species-specific things, normalizing your forces and energies in particular ways, predicting energies not as just the raw number coming out of the simulation, but relative to the energies of isolated atoms. So there's all these little things really do add up.
If I can make a historical
Yes.
machine learning comment.
Please.
In the old-fashioned days of speech recognition.
Yeah.
Where people were using hidden Markov models primarily to do the work. A major advance was, I believe, climbing on performance rather than the maximum likelihood of the data.
Okay.
Right?
Yeah.
I mean, I still don't quite understand why that was a good idea, but it definitely was a good idea.
So you're saying like just changing the metric by which they were
Yeah, I mean,
training the
come
model?
on, some level, have the metric what you really want.
Yeah. Yeah.
And that may be a good idea.
Yeah,
Mhm.
yeah. So I think definitely in the case of like delta learning, this is a good way to do it kind of for that reason, because we don't really care about the absolute energy of the material. We just care about the relative energy compared to the isolated atoms. So I think that's kind of part of it. But I think there's an even deeper aspect of that. We could have a much longer conversation about that. Yeah, so there's that one. I go till 3:45, but I want to also leave some time for questions. So maybe 5 more minutes. Okay, let's do some generative model stuff. I'm going to skip some slides about spherical harmonics, and you can ask me questions about them later if they look tantalizing. This is actually pointing back to what Trevor was saying about SOAP kernels. SOAP kernels are basically based off of these projections of delta functions. Well, in SOAP's case, they're smeared Gaussians, but essentially projecting delta functions onto spherical harmonics. This is essentially what's under the hood when we're doing our convolutional filters. But I'm going to skip this part. What I really want to point out here is that spherical harmonics are useful, and they are useful for generative models where you want to predict atomic positions. So we have this nice little autoregressive model called Symphony because we have, spherical harmonics, and so it's a symphony of spherical harmonics. It's very corny. But the idea here, so autoregressive, meaning in the same sense of you're interacting with ChatGPT and it's producing tokens one at a time. We're producing atoms one at a time. So you start with an atom, add another one, and so forth. But we break down the prediction step into several sub-predictions. First, given a fragment, the atoms vote and they say, who wants a neighbor? And so they vote, and this guy gets a neighbor. And they say, okay, what type of atom do you want? Okay, it wants a hydrogen. Great. Then we predict the distribution of possible positions for that hydrogen atom, and then we sample. And so this is going to be stochastic, but it has a lot of several nice properties. So we're using spherical harmonics to express this spatial distribution. So in this case, it's kind of like using spherical coordinates in a way, because we have this origin for our density prediction. We're still under the hood using Cartesian, but I think it gets to kind of what you were saying. What is really nice is that sampling is going to be symmetric. So if I take this fragment and put on this hydrogen, I am guaranteed to be just as likely to put down this hydrogen first before I create this CH4 molecule. This is just a nice property to have, especially as you start building bigger things, because then it doesn't need to see building it this way and this way. It understands that that's equivalent. Yeah.
Like the mass.
Yeah, so this is actually done with teacher forcing. So we break it down, so we come up with arbitrary ways to build the molecule. And then so we are actually only training one step at a time. And then on inference, you're chaining these steps together. So basically we'll say, okay, it has to predict this one, and then it has to predict this. And so we've actually broken it into a bunch of little things in order to do it. So it kind of makes it nice and chunkable so that we're not backpropping through this entire prediction. And that seems to work pretty well. Okay. One more generative model, so that's Symphony, and we're kind of improving upon it, making it faster, stronger, all those sorts of things, bionic manish. Let's talk about proteins. I really love this autoencoder. This is work with Joe Jacobson's group in the Media Lab. This is a vanilla autoencoder, so it's not a variational autoencoder, it's a strict autoencoder, but we're doing it on proteins. So we have some protein structure, we have an all atom representation, we put everything onto the alpha carbon, so every amino acid in the protein has an alpha carbon, so we first project everything onto the alpha carbon, and then we're treating it kind of like a sequence, but we're still keeping around a lot of geometric information. And the goal here is to essentially trade geometric degrees of freedom for feature degrees of freedom. So what we're doing is we start off with all the amino acids, and then we're kind of chunking them. So if I have, a sequence of amino acids, I am going to coarsen the first three into this amino acid, the next, or into this coarsened representation, these three into the next coarsened representation, and these three into the next one. And so this becomes the input for the next layer. So we're slowly kind of eating up the beads on this protein, and then we do the reverse. So we go all residues, coarsened residues, even more coarse, we get to one single point with a bunch of tensorial features on them and go back.
We have the unit.
Mm-hmm.
It has these residual connections.
Yeah, so we don't have residual connections between, in this case. This is yes, but you could totally do something like that as well. In this case, what we're trying to do is to not bring it through like a statistical bottleneck, but a representational bottleneck, saying like, if I kind of give you the same number of parameters, but I'm forcing you to represent it this way, what do you do? And what's nice, you can actually train a separate generative model to generate in this space and then use the decoder to go back to all atoms. So we have trained like a diffusion model to generate proteins this way and then back out. It works okay. It could be better. What is really cool about this encoder is the latent space. Specifically, you take two different conformations of the same protein. So proteins are little molecular machines, and they are opening and closing and doing all sorts of things, and they move in all sorts of fantastic ways. So you can have a protein, and you can have like this protein here. It's kind of closed, and then it opens. And there's even like a disordered region here. And this one also sort of opens and closes, but it does it in this weird twisty way. The key thing is that if you were to just take this structure and linearly interpolate the coordinates, it would be a hot mess. It would not be physical. That is not what this distortion looks like. However, if you interpolate in the latent space, this is the distortion you get. And it is something that if you check kind of all your usual metrics for the fitness of a protein, like clashes and bond and angles between different residues, it actually looks physical. And we didn't train it to do that. We just trained it to auto-encode proteins. It seems to be that there's something nice about this representational latent space when we do coarse graining. So I'm interested to see in the future, does this transfer over to other atomistic systems? Can we see these nice sort of deformations in other data sets as well? Okay. I'm out of time. The catch for these models is that tensor products are expensive. And we wrote a paper about that, and that I'm happy to talk about if that's of interest. Essentially, it's a little bit complicated, and there's a lot of confusion in the literature as to why tensor products are expensive, and we tried to clear that up. But I won't talk about that now. What I will say, hopefully that goes to that one. What I will say is that I am honored to have a really awesome research group that does amazing things and keeps me sane. So we are the Atomic Architects. We're in AECS in the Research Laboratory of Electronics. And this is us on our second annual winter retreat going skiing. We have some amazing collaborators who we get to work with to keep science even more fun. We have very nice funding resources to keep the lights on. And then I'm going to leave these takeaways, and I'm happy to answer any other questions that you have. Thank you for your time.